All right, we are recording. Good. All right. Hello, everyone. This is Christian recording a video for a practice exam for Chem 1, your first exam. Here's some information that we'll be going over real quick. Uh, your pre-exam checklist. What's necessary to bring is at least one calculator. Oops, it's on an eraser. One calculator and one writing utensil. So make sure you have your calculator. Make sure it's scientific. Make sure it's not graphing. And make sure you have at least one thing to write with, because trying to do all this mental math, it's going to be painful. So that's all I can say. What I do recommend you bringing, though, again, this is like worst case scenario. What I recommend, again, calculator. I use the TI-30, works for me. Really good scientific calculator. 2 to 3 pencils. Make sure that they're all sharpened before you get there. You will run through pencils during the exam, like they'll get dull over time, unless you have a mechanical one. Again, I use wooden pencils, but if you have a mechanical one, it'll probably last you longer. Recommend bringing a dedicated eraser. You don't know how much erasing you're going to be doing. I actually do a lot of erasing. My pencils, like the eraser that they have, dries up real quick, so I'd recommend bringing just one slab eraser. And what I recommend is just worst case scenario, just have one pen. It's reliable. It always has. Make sure that it has a lot of ink, and no matter what, you're not gonna. Typically, you won't run out of ink during the course of an exam. General exam tips is to make sure for sure that you know your CougarNet ID and password before you go into the exam. You have to log into the computers in the testing center, so make sure that you do know those. If you don't know your password, you're kind of cooked, because I just checked the exam reservation, and I think except for like Monday at 9 a.m. and Monday at 10:30, I think all the spots are filled up. They might open some more spots later on, but just make sure for sure that you know this. Make sure you've done your biometric scan, especially if this is your first exam. Just I'd say go in the day before. Let's say your exam's on Tuesday. Make sure you do your biometrics. If your exam is on Monday, I'd recommend just going there as early as possible to do your biometrics before you come in to do your exam. Take your time on your questions. Don't get stressed by the clock. The clock is always running for everyone, so just keep a good pace, I guess. Skip questions that you don't know how to do. It's better to do questions that you do know how to do and get the points for those than to be stuck on a question that you don't know how to do and end up running the clock before you can get to those questions you do know how to do. Your first exam is at Casa Garrison. Do not show up to the wrong testing center. If you show up to CBB and you're like on time, right? Like let's say your exam's at 9 a.m. on Tuesday, and you show up at CBB, you're like, yes, I'm ready to take this exam. I studied all night last night. Feel so ready, and you're at CBB. Now you have to run 15 minutes. In 15 minutes, you have to run from CBV to Garrison. I'm not saying it's impossible, but you know, you don't want to be sweaty and tired and show up to your exam. And this one is very important. Do not try to cheat in CASA. There are at least 3 cameras on you at any given point in time. It is better to fail this exam than to get a 0, have to stand before an academic honesty committee, and have a mark on your UH transcript. You will not get away with cheating. What's his name? For the biology and biochemistry department. The guy who runs that is Dr. Franchino. I don't know who runs it for Chem, but I had Franchino as a professor one time for a class, and he spilled the tea on what happens in CASA. So, just know this: like, do not try to cheat at all. All right, I'd rather y'all get like a 30 or 40 on this exam than take the L because of cheating. Here's what is allowed. This is called info dumping. So let's say you studied everything except for your polyatomic ions because there's so much of them. What you can do is show up to Garrison 30 minutes early, right? Memorize your polyatomic ions or whatever you need to memorize, just memorize it. And then as soon as you sit down, you're gonna write everything, absolutely everything, onto your piece of paper that they give you. And somehow this is allowed. I mean, use it to your advantage if you need it. That's what I recommend. Here's how I recommend studying if you're only starting to study now. Wrong move, definitely. Especially if your exam's on Monday. Strongly recommended you started studying last week. First of all, you're gonna go through your chapter summaries on Teams. Recommend going through that. Just see what you know, what you don't know, what you're familiar with, what you're not familiar with, right? Rewatch your Tom T YouTube videos on topics that you're weakest at, and then after that, make sure that you kind of have a general knowledge of everything. Make sure that you're kind of prepared, and then I'd recommend doing your practice problems. One place that I'd go to look for additional practice problems is the UH Science Resource website. I think they have 2 to 3 old exams on there, so I recommend that. Next is your past worksheets on Teams. I've posted pretty much all of the worksheets. I think I forgot to post this week's, but I will be doing that as soon as I finish recording this. Next, you're going to go over the homeworks and quizzes that you scored the lowest on. I think you'll be able to see like kind of where you're weakest, where you're strongest. And, collect all your practice tests, like I said, also from UH Science Resource. And save the one on Canvas for last, because that's probably as close as you're going to get to the actual exam. You can read through this. This is just kind of my recommendation on how you should study your practice exams. You want to improve with each practice exam. You don't want to just be going through them willy-nilly and just throw them away, right? They're valuable practice. If you have time, here are the things that are typically not memorized by a lot of students. Have you memorized your polyatomic ions? Your SO-CoClone-Os, SO4 2 minuses, your CO3 2 minuses, your COO4 minuses, and your NO3 minuses. Make sure you know those. Go over the definitions of each quantum number. What does N mean? What does L mean? What does ML? What does MS mean? Right? And then go over your theorems, right? Like law of conservation of mass, and who was the one who said the law of conservation of mass, right? All right, let's get into the exam. There's a periodic table here. We're gonna be getting into that soon, and I don't know if you're allowed to draw on the periodic table, but just as a quick summary. Actually, we'll do that when we get to the questions. First question: how many significant figures are on each of the calculations on measured values, right? So for multiplication, we know it's least number of sig figs. We have 4 sig figs here. Remember, trailing zeros are significant. 4 sig figs here. So if we're multiplying 2 numbers with 4 sig figs each, we have 4 sig figs for our answer. And they're not asking us to do the math. They're just telling us, okay, how many sig figs are there? Here we have addition, right? And for addition and subtraction, it is based on the number of decimal places. Here we have 4 decimal places. Here we have 1. Here we have none, right? So we know that we're gonna have 0 decimal places. You do all this math, right? And you'll get 30,000 something or other, right? And 30,000, that is 5 sig figs, right? So we have 5 sig figs here. And again, you can plug into your calculator and just ignore the decimal places, count those, and you'll get this answer. What I would keep in mind though is, for whatever reason, if you have 36,410, right? This is considered like -1 decimal places. So if you're doing addition, you should count this as -1 decimal places. Oops, my screen froze. Hello? No. No, why did it disconnect? Oh my god. Alright. Say hello to my beautiful wallpaper. Oops, wrong app. Alright. Let's get back to work. Recording. Okay. Sorry for that. So, we understand these. I'm not going to go over them again. Hopefully y'all understood that. Next, use scientific exponential notation to express the following quantities in terms of the given SI base units. So here, you know that scientific notation is where you have one number in front of the decimal, that blah, 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 blah. Usually there's 2 numbers. Here they only had 1 for whatever reason. But, that's kind of how you want to do it. 1 point something, like let's say, I don't know, 0, 0 times 10 to the whatever. Right, so for this, hopefully you've understood your units. You know that 1 micrometer, let me erase this, equals 1 meter. Or the 10 to the -6 meters. Sorry, my bad. So what we're going to do here is we're going to have 74.5 times 10 to the -6 meters. However, this is not what the question is asking us. So what we're going to do is we're going to move this decimal place over here. And what that means is we have a smaller number here, so we can have a bigger number here. 7.45 times 10 to the -5 meters. Perfect. Perfect. Exactamundo. Identify the mass law that is demonstrated by the following observation. I was about to say observation. That was crazy. Mass ratio of arsenic to oxygen in one compound is bleh, and the mass ratio of arsenic to oxygen in another compound is bleh. So obviously we're dealing with mass ratios, aka proportions. And we can see that there are two different proportions, and you can say that two proportions are multiple proportions. So our answer here is the law of multiple proportions. And to get an idea of what each of these mean, definite proportion just means that H2O will always have two hydrogens and one oxygen. Conservation of mass is basically saying H plus OH goes to H2O, right? What we're saying here is there's not going to be a mass change, right? If you were to sum the mass of one hydrogen and the sum of one hydroxide, you will always get the mass of water, right? You're not losing mass. Mass is neither created nor destroyed. And this is just saying it's both of these. Clearly it's not. So our answer is C. How many neutrons are there in the nucleus of 108 Ag? This is where we're going to go to our periodic table. And then we'll give you a periodic table in the exam. You don't have to worry about this. They're not going to ask you to memorize a periodic table. Ag is right here. 47 is right there. That's our atomic number. So our missing link to this is the atomic number, right? We know that mass number equals atom number. This is our atomic number. This is our mass number. Remember that atomic number is the number of protons plus number of neutrons. So we plug in our numbers. 108 equals 487 plus some number. And we can just do math and subtract 47 on both sides, and we should get 61 neutrons. My handwriting is garbage. I am so sorry. Cool. Next. Fluorocarbon is known to contain only that. First sample has that. Second sample of the same fluorocarbon. Let's use a different highlighter. The same contains that much of carbon. So this is going back to this question. We have the law of definite proportions on this question. Not question 3, right? But for question 5, we're using the law of definite proportions. So, if we have this, right? So, if we know that this is a different proportion, we know that converting carbon to this amount means that the same conversion will be used, right? So, from 14.40 grams of carbon to 59.50 grams of carbon, we're going to use the same thing for our fluorines and our hydrogens. So, let's just write this down real quick. There's a fluorine and blank chlorine. And we have hydrogen at 2.4542. So let's keep a sum total over here. And this is where we're going to put our answer. We have 59.50 grams of carbon for sure. So let's divide 59.50 by 14.40. Just get your calculator out. 59.50 minus 4, divided by, 14.40. And for that, we're multiplying by 4.13. So we're going to multiply each of these by 4.13. And the reason why we're multiplying is because it's proportional, right? We do the mass on fluorine, calculator. And again, I'm plugging these into the calculator. It should be about the same pace that you could probably go on an exam. Should get that number. Hydrogen. Get 10 grams of carbon, or hydrogen. You plug these in here, 10.45 grams of fluorine, 5, and 10.00. You sum those up, again, plug it into your calculator. We should get 79.95 grams of fluorocarbon. And that is our answer. Alright, let y'all sink that in. All right, how much energy does a photon of light with wavelength of that have? So we know our two equations for this, right? We have lambda, which is our wavelength, times frequency, which is our frequency, or I don't know what this Greek symbol is, but someone can tell me later on. Equals speed of light, right? And we also know that energy equals speed of light, or times frequency. We're gonna use these two equations to find the energy, right? So we're gonna plug this equation right here down into here. So our E equals, again, if you have frequency equals C over lambda. Again, we're just dividing both sides of these by lambda for wavelength. So we're going to plug that in here, and we should get H times C over lambda. So how much energy does this have? We're going to convert this right away, just so we don't get confused. 654 times 10 to the negative 9. Remember that nano is to the negative 9 meters. So let's plug in our numbers. H, again, that's on the periodic table. We can scroll up and check it. H should be right here, Planck's constant. 6.626 times 10 to the power of negative 34. And I believe that's joules times seconds. Speed of light, also on your formula sheet, 3 times 10 to the power of 8. Divide that by our calculated wavelength, or the wavelength they gave us, 654 times 10 to the power of negative 9 meters. Perfect. We can start canceling out units. Meters divided by meters. Seconds divided by seconds. That's 1 over seconds. That's why we can do that cancellation. We get joules, which is the unit for energy. So perfect, all right? Plug that into your calculator. And I recommend keeping the parentheses in your calculator. That just prevents you from doing wrong math. 6.626 times 10 to the power of negative 34 times 3 times 10 to the power of 8 divided by 654 times 10 to the power of negative 9. We do get our answer. Plug that into our calculator. We get 3.04 times 10 to the power of negative 19 joules. Very tiny number. Part B is actually easier because we're only going to be using this equation. What is the frequency of this light? So they already gave us wavelength, right? So frequency, we know from our previous equation, is C over lambda. So we know that C 3.00 times 10 to the power of 8 meters per second, all over 654 times 10 to the negative 9 meters. Meters and meters cancel out. You get 1 over seconds as our unit, which is equal to hertz, which is the units that we're looking for. So that's like a tip right there. If you're doing these like kind of math problems, you want to make sure that your units match up at the end to what you're solving for. In this case, it's 1 over seconds or seconds inverse, which is correct. 3 times 10 to the power of 8 divided by 654 times 10 to the power of negative 9. Boom. We should get this answer, which is 450. Again, I plug it into the calculator. 4.59 times 10 to the power of 14. Oh, seconds inverse. Typically, they won't make you plug in the units. They might, but just make sure you know what units you're using. Let me box this answer too. Cool. Draw an orbital diagram for boron. Again, okay. So here's the fun part where we're gonna start labeling the periodic table. We know that this is the s orbitals, and that helium's part of it too. That's our s. This is our s. Next orbitals are the p orbitals, and I just remember the order of SPDF. You know, I think that makes life easier. Oops. Very roughly highlighted. We know that this is our p orbitals. I don't think you'll be allowed to highlight these in the exam, but I'm just gonna do it. I don't know if you're allowed to, mess with the periodic table that they give you. Oh, LA. Remember that LA is part of the f orbitals and AC as well. And remember that LU and LR are part of this orbital. So these are our d orbitals. These are d orbitals. The rest are our f orbitals. Let's use purple. Epic. So f orbitals right here. We see borons right here. So it's 1s2, 2s2, and 2p1. Let's write that. 1s2, 2s2, 2p1. So we know that we have 2 electrons in our 1s orbital, 2 electrons in our 2s orbital, and 1 electron in our 2p orbital. And just know that these are 1 orbital each. These are 3 subshells, basically. Subshells and orbitals are kind of used interchangeably. That's what I've kind of learned from reteaching chem. So just keep in mind. You have to kind of look at the context. And how they'll make you answer this question is they'll have this energy diagram here. This says energy on it. If you're 1s, if you're 2s, and then you have your 2p. And they'll already fill this out for you, right? This is 2pz, 2px, 2py. So you just have to fill in our electrons, right? 2 electrons here, 1, 2. You know that 2 electrons can fit in one of these. 2s has 2 electrons, and we find our electrons from the exponents. And we only have 1 electron here, so just fill that in. And that'll be your answer. Like I said, they'll already plug this in for you. All you need to do is put in the electrons. Cool. 8. Calculate the frequency of light emitted by a hydrogen atom. So emitted means we know it's a negative number, especially for energy. We know that frequency and energy are not inverse of each other. They have a direct correlation. So we know that if we're emitting frequency, we're also emitting energy. So our energy number should be negative at the end, right? And for whatever reason, they give you all this number. So I don't have to worry about memorizing that equation, I guess. But I'd still memorize it just in case. We know that this is going to be 1n squared minus 1n squared. And if you're kind of forgetful, like me, on which one's final minus initial, here it says we're emitting. So we want this number to be a positive number because we have a negative number here, if that kind of makes sense. And we know that this can become a positive number if we do 1 over 1 minus 1 over 3 squared, right? This will result in a positive number times that number, right? So in that case, if 1's down here, this is a final minus initial. We can put in this number here, negative 2.180 times 10 to the negative 18 joules times that. And again, we don't have to put units for n's. Those are just numbers, basically. You do the math. Wait, pause. Let me put it here, because we still have more work to do after this. Negative 2.180 times 10 to the power of negative 18 times 1 over 1. Again, I'm just plugging this into my calculator, not doing anything fancy. We get negative 1.938 times 10 to the negative 18 joules. And we remember the equation from up here? E equals h times frequency. And we're looking for frequency, right? So if E equals h times frequency, the frequency equals E over h. Energy equals frequency over h. So, we're solving for frequency, my bad. Frequency equals E over h. Let me make this better. So we just plug in this number, negative 1.938 times 10 to the negative 18, all over h, which we know is 6.626 times 10 to the negative 34. And again, this is joules. This is joules times seconds. Cancel out the joules. 1 over seconds is our unit, which is correct for frequency. Plug that into our calculator. 6.626 times. And I'm just using the answer function, so I don't have to plug in that number again. Alright. We get negative 2.92 times 10 to the 15 inverse seconds. And you can't have a negative number for frequency, so we're just going to have that number. Because the reason for that is we know that energy is being emitted. So if you say that this frequency of light is emitted, it's kind of implying that it's negative. Just a, I guess, English / chemistry / math, like, conundrum, I guess. All right, so that's how you get that number. And remember, we're looking for frequency, not energy. That's why we have to do all that calculation. Two-step problem. Next is, which of the following subshells fills first in a typical polyelectron atom? So we're given all these information. And obviously the answer for this in a broad sense is the 1s or subshell, right? Unfortunately, they don't tell us that. So we have, let's just like keep going down the list, right? 1s2, 2s2, 2p6, 3s2. Let's just like, a theoretical atom, right? p6, 4s2, 3d10, 4p6, and I think that's pretty much everything that's been shown up, except for the 4d. So we know that 4d is definitely not going to be first, because we didn't even get there before we got the rest of these. So we have our 2s orbital here, our 3s here, and our 4s here. Which one of these fills up first? Well, clearly it's the 2s, because it's earlier in the line. And remember that they'll always fill up electrons from lowest energy to highest energy. Next. What is the maximum number of electrons that can occupy the orbitals within the n equals 4 subshell? Okay. So to get this answer, we know that 4 when n equals 4. I believe there's like an equation to this. I forgot. But how I'm going to solve this is we know that ml equals 3, right? Or 0, 1, 2, and 3. For that, so we have s, p, d, and f orbitals, right? S, p, d, and f. Each of these holds 2, right? Or no, not 2, but each ml equals -3 and -2, -1, 0, 1, and 2, and 3. And we know each of these can fill up 2, right? So here at 4, we have 4s, 4d, 4p, 4d, and 4f. For 4s orbitals, we have we can hold 1 subshell, right? That's 2 electrons. We have 3 here, we have 5 here, and we have 7 here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 of these orbitals. Each orbital can hold 2 electrons. So we get 32 electrons. I hope this kind of makes sense, right? Basically what I did was I said, like, okay, n equals 4 can hold this. We can hold the 4s orbitals. We can hold the 4p orbitals. We can hold the 4d orbitals. We can hold the 4f orbitals. And in this case, we have basically all those. We have all these subshells, right? Or, I guess, orbitals. And each orbital can hold 2 electrons. Orbital subshells are confusing. They kind of use them interchangeably, which blows my mind. But 32 is the correct answer. There's a formula for this. I believe Chelsea went over it in class, but me personally, I forgot. So if you're forgetful like me, this is how I would do it. How many H orbitals make a 6H subshell? Dang. So here, instead of the electrons, we're just using these, right? There's kind of a trend to this. You're starting from 1, and each time you go up, it's +2, +2, +2. You get it 1, +2 is 3, +2 is 5, +2 is 7. And we know that subshell designations are alphabetical, right? So S, P, D, F, A, B, C, D, E, F, G, H, right? So S has 1, and remember +2, 3, 5, 7, 9, 11. H is 11. 11 is our answer. Nice, quick, and easy. Which of the following statements about quantum theory is correct? The energy and position of an electron cannot be determined simultaneously. This is actually true. If you thought this was false, this is actually true. Because as we know from the Bohr equation, which kind of has to do with this orbital diagram, we know that we can excite, our electrons can be excited to multiple energy levels, right? So even though they'll fill a lower energy orbital, they can be excited to multiple states. So we cannot determine this, energy and position simultaneously. So this is true. Lower energy orbitals are filled with electrons before higher energy lower energy orbitals are filled with electrons before higher energy orbitals. We know this is true. Like how we do the 1s2, 2s2, 2p6. You go from the lowest to the highest. When filling orbitals of equal energy, two electrons will fill the same orbital before filling a new orbital. This is false. Remember? That's why when we have, like, let's say our 2p orbital, right? 1, 2, 3. If we were going to fill this up completely, we go 1, 2, 3, 4, 5, 6. We don't fill that. We don't do 1, 2, 3, 4, 5, 6. That's incorrect. So that's how we know this is false. Let me make that F better. No two electrons can have the same four quantum numbers. That is true. For instance, if we use our 2p example again, let's say we have these two, or let's say we have these two electrons. If we're comparing these two or these two, they'll all be different, right? For this one specifically, it is n equals 2 because it's a 2p orbital. L equals 1 because it corresponds to p. ML is equal to the first number, which is -1. This is -1, 0, 1, by the way. And then MS, we know it's a positive spin, so plus 1/2. If we were to compare it to this orbital, we know that this is n equals 2 as well. L equals 1 as well. L equals -1. And we know that MS is downwards -1/2. So they'll never be the same, right? Or I shouldn't X that out, but you should see that these are not equal to each other. Or is it this way? I don't know. Something like that. So this is true. And then, of course, we have one that's false. So not all these are correct. Or it's kind of ironic, but the answer is C. Fe has blank in its d orbital. So let's go back to our periodic table. Fe is right here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. We know that our highest is 3d6. Go back to this all the way. Dang, we've gone through so many questions. D orbital, and we know that it's only orbitals it's only d orbitals is the 3d orbital. We know it's 6. We know the 3d is 5. Has 5 orbitals. Right. So if we're gonna do 6, 1, 2, 3, 4, 5, 6. Right. So we have how many? 4 electrons that are unpaired. These don't have a buddy. This one has a buddy. These do not have buddies. So 4 electrons. Might work. Which of the following is a nonmetal? I mean, I have the. Let me just go. Okay, so just memorize those as I peek up. So SR. Where's SR? Again, this might take some time. SR. I'm so sorry that I'm blind. Unfortunately, I cannot see. Oh, SR is right here. Let's use a weird color. Let's use purple. SR, or no, I feel like, let's use the color palette thingy. Let's use a pink. That way it sticks out from everything. SR is right here. Oh, let's use a, there we go. SR is right there. Next is SE. SE is over here. SC. SC is, where is SE? SC is right here. We have SN. Oops, oh, I changed color. And we have CS. Where's CS? I'm so sorry that oh, right here. So as you'll remember, these are your, oops, let me return this to 5, because that's what I prefer. And let's use black. Or I was using blue. So CS, we know that this is the alkali metals, right? Let's use M for or just met. We know that these are metals, right? And CS is one of them. So we know that CS is not the correct answer choice. These are our alkaline earth. I'm just gonna put E mets. Our alkaline earth metals. So SR is definitely not an alkaline, or it's definitely not a non-metal because it's one of the metals. We know that all these, basically our entire D and F orbitals, are transition metals. Let's just use mets. Alright, so this is clearly a metal, not. And here's where it kind of gets interesting. As y'all remember, there is like it's kind of like a I forgot how the thing goes, but I'm pretty sure like goes down here, goes here, goes here, goes here. I'm pretty sure this is how this works, but God bless that they're not right next to each other, right? And all of these, I'm pretty sure it's boron, silicon. I think these are all metalloids, right? Something like that. But Sn is clearly on the metal side, so we know it's not that. And Se is clearly on the non-metal side, so we know it's Se. Where is Se? Oh, we've gone through so many questions. Crazy. We know it's Se. That is our answer. Of the following, which element has the highest first ionization energy, i.e. 1? Alright? Oh, memorize these elements, I guess. Yeah, we're gonna go back up. I'm just gonna erase this whole thing. Because I need to highlight more stuff. Hopefully, you all have taken a good look at that before I deleted it. We have aluminum, which is Al, right? Al is right here. Magnesium, Mg, is right here. Sodium, Na, is all the way on the left. And silicon is over here. So we can see that they're all kind of in a row, right? So first ionization energy is kind of how hard is it to take away that first electron, right? So usually at carbon, right? We know that carbon is usually non-metal and usually gives away its electrons too, or it usually shares its electrons, right? We know that O is usually 2 minus, right? N is usually 3 minus. Fluorine is usually minus. So we know that fluorine, it's really hard to take away an electron, fluorine, because it really wants to grab an electron, right? Um, so typically, these the more right you go, the harder it is to take away an electron. Oxygen too, like it's hard to take away an electron from oxygen because it just wants to grab 2 electrons. So the one that's farthest to the right is the correct answer, which is silicon. We're gonna go back down. Silicon, silicon. There's our answer as our highest first ionization energy. Because farthest to the right, we know that the easiest one to take away is sodium, because sodium really just wants to give up that electron to form its octet. Remember that all this is in the name of getting octet. For the following atom, identify the number of core and valence electrons, and write the electron configuration of the valence electrons. We have Cl. I'll take a trip to the periodic table. Cl, right? 1s2, 2s2, 2p6, 3s2, 3p5. Let's just keep that in mind. 3p5 is our highest. 3p5. So we'll just finish this. 1s2, 2s2, 2p6, 3s2, 3p5. There we go. So we know that the valence electrons are the ones that contribute to octet. In this case, it'll be 3s and 3p orbitals. That or the electrons in them, and these are our inner orbitals, right? So our core electrons, we have 2 plus 2 plus 6, right? 2 plus 2 plus 6, that's 10. Valence electrons, 2 plus 5, that is 7, because these are the ones that contribute to binding. Valence electron configuration, well, it's only the valence, right? So we only have to plug in this here, which is 3s2, 3p5. Hoping that made sense for y'all. Cool. Alright, let's move on to the next one. Based on electronegativity trends in the periodic table, which of the following compounds have the greatest percent ionic character? So we know ionic is, your one usually the negatively charged, right, is just straight up getting electrons from the positively charged, right? So like for instance, Na plus Cl, right? Na becomes positive, Cl becomes negative because Na is just gonna give up its electron, right? So predict which of the following will have the greatest percent ionic character. So let's just memorize this list again. I'm so sorry that I don't have periodic tables on each question. We'll just memorize that list. Let's erase this real quick. So we have all of them have something all of them have in common is Sr. So I think this is going to be our metal for all of them. Oh, H as well, right? H and Cl, right? So we have Cl, we have iodine, we have chlorines, like we said, fluorines, and we have more chlorines. Okay. So percent ionic character depends on the distance from the metals to the non-metals, basically. And we know that fluorine is basically, aside from the what's it called, these you know, let's ignore the noble gases. Fluorine is basically the most electronegative, right? So that's kind of a big gap. And you might think, so that's pretty much going to be our answer, right? SrF2. But you might think, oh, well, what about HCl, right? Um, it's diagonal across the table, not horizontal, right? And as you can see, diagonally, I think Sr is farther away. I don't really know how to explain why it's not HCl, but just know that I think the best way to kind of think about it is H hydrogens can sort of be the metallic ionic thing. Like, for instance, and HCl is definitely acting as kind of a metal here, giving up its electron to Cl. But you also have to remember, like, we also have compounds like CH4, where, hydrogens are kind of acting as because this is covalent, right? We know that hydrogens are sort of still acting as a nonmetal. So that's why we know it's going to be Sr. And if you pull up the, what's it called, um, the electronegativity table, I don't think they'll give it to you. Um, so if you pull that up, you can see that the difference in electronegativity is greater between Sr and F than H and Cl. Oh, there's also calcium. Whoops. There's also calcium. But you can see that calcium is closer to them than Sr, so kind of the same deal. So we know that our answer is SRF2. Calcium reacts with phosphorus to form blank. So we know that Ca is 2 plus, and phosphorus is P 1, 2, 3. P's can go 1, 2, 3. And again, we're getting these charges because they want to go to noble gas configuration. And I'll explain that in a second. So basically, let's erase this periodic table again. Sorry. Erase this stuff. Calcium wants to form, everything basically wants to form noble gas configuration. So to do that, calcium needs to lose 2 electrons. When you lose 2 electrons, calcium becomes Ca2+. I hope that makes sense. You're losing 2 electrons, you have 2 more protons than electrons, so you have a 2 plus charge. Phosphorus, well, it's easier for phosphorus to go this way than it is to go that way, so it's going to prefer just grabbing 3 electrons. If you're going to get 3 more electrons than normal, you're going to have a P3 minus, right? 3 minus charge. And the idea between this is you want to this is a plus, 3 minus. You want to equivalize, I guess. I don't know the English word for this. You want to make the charges equivalent, right? Cancel out. So we're going to want 2 phosphoruses, and we want 3 calciums, right? Because 3 times 2 is 6, and 2 times 3 is also 6. So we want 3 calciums and 2 phosphoruses, and how I've explained this is, the easiest way to do this is just put the charges down here, right? So we're going to get Ca3, P2. And which one matches that? This one right here. Cool. Making good progress. After an atom has lost an electron, it becomes a blank and has a blank charge. So clearly we can already clear some of these out. Isotopes have nothing to do with electrons, right? That's a different number of neutrons. And compounds, what are even those, right? So when you lose an electron, right? So let's say Na, right? Na is going to lose an electron, right? It's going to become positive. Well, positively charged ions are, as we know, cations. And so it's clearly not any of these. So it's cation, right? And we know it's positively charged because there's a plus here. Lewis structure for elemental nitrogen, there are blank. So let's do this the long way, right? Let's actually draw the Lewis structure. We know that nitrogen has 5 valence electrons, you can go up to the periodic table, see that it has, right, 1, 2, 3, 4, 5 valence electrons. And we have 2 of them, so there are 10 total valence electrons. We have our Lewis structure. Let's just put these together, and let's use one bond, right? So we know that with that one bond, we're losing 2 electrons. We have 8 valence electrons left. So 1, 2, 3, 4, 5, 6, 7, 8. Oops, we didn't fill the octet here. So it's clearly not that. Let's try a double bond. 8 valence electrons, right? 1, 2, 3, 4, 5, 6. Oh, whoops. 1, 2, 3, 4, 5, 6, 7, 8. Right? Am I doing this wrong? No, 10, and we do a double bond, sorry. There are 10 still, sorry, my bad. 5 valence electrons times 2, 10. We have double bonds, minus 4. We have 6 electrons left. 1, 2, 3, 4, 5, 6. You still don't have an octet in here, so it's probably not this one, right? Because there's no charge here. There's no positive or minus. So let's do a triple bond. We're using up 6 electrons in the triple bond. We have 4 electrons left. Bada bing, bada boom. We have full octet, right? This nitrogen has 6 electrons from here, and it has 2 electrons from here. 6 plus 2 is 8. Same for the other nitrogen. So I think this is a correct Lewis structure, and to double check, we can formal charge it, right? Fc equals it's what's it called? Number of valence electrons minus sticks minus dots. So for this nitrogen, right, we have 5 valence electrons on one nitrogen, minus 3 sticks, minus 2 dots, we get 0. This nitrogen, same thing, 5 minus 3 minus 2 equals 0. So let's see which one's the correct answer. A single bond, we tried that, did not work. Double bond, tried that, did not work. Triple bond, that is the correct answer. 3 unpaired electrons, well, we don't have 3 electrons just floating in space. So, not that one. And it has an answer, so none of the above. We're almost there. We have like 3 questions left, right? In thional chloride, they give it to you. S is the central atom. So let's just, SOCl. What is the formal charge on the oxygen and number of lone pairs on oxygen respectively, right? So the HCl, right, we can go up to the periodic table. I think I've had enough of scrolling up and down. So, we have 2 Cls, 7 plus 7. Sulfur has 6 valence electrons, and oxygen also has 6. 14 plus 6 is 20, 26. Now let's try this. Let's do one bond on each. These are 26 valence electrons. Let's say we have 3 bonds, right? That's going to be 20 left. Let's try and fill this up. Remember, we want to fill the outside ones before we fill the inside ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, we filled the octet, right? Looks like we're good, right? We have 0 electrons left. We've used up all 20. Now let's do formal charges, right? And to make sure, remember that this is a neutral atom, so let's make sure that it's actually the correct one, right? So chlorine's right. 7 minus 1 stick minus 1, 2, 3, 4, 5, 6 dots. 0. You can apply that to the same chlorine. I'm not going to do that math. Oxygen has 6 valence electrons minus 1 stick minus 6 dots. Oh, we have a negative 1 charge. There might be an issue here. 5. For our sulfur, we also have 6 minus 3 sticks minus 2 dots, and equals plus 1. And you can see that these cancel out, right? Now you might be thinking, okay, well, why can't we just make it cancel out better, right? Sulfur, let's say we double bond the oxygens, right? This is just an example. In this example, we'd have 1, 2, 3, 4. That'd be 8. So we'd have 18 valence electrons left, or 18 electrons left. Let's try filling that in, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Well, we have 2 left over electrons. We can't have that. So that's why this one does not work. As you can see, our oxygen has a formal charge of -1. So it's one of the -1 ones. And we can see that we have 1, 2, and 3 lone pairs. So, oops. I plugged sorry. This should be 3. I promise. Trust me. This should have -1 and 3. And that's the correct answer. Because it wouldn't make sense to have -1 and 1 for both. That was just me typing it in wrong. My bad. Let's do questions. Formula of tetraphosphorus trisulfide. So I'd recommend that y'all memorize, what's it called? So mono, we have di, we have tri, we have tetra. Then the rest, y'all kind of have learned it. Penta, hexa, and then for 7, it's hepta, 8 is octa, 9 is nona, deca. And I don't think you'll need to know more than that. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So tetra is here. So we have P4. Sulfide is an S. P4, S3. And we know that it's going to have if it has the numbers on it, you know that it's just elemental. It's not going to deal with polyatomic ions and stuff. Alright, so that's our correct answer. Easy stuff. I think everyone should be able to get that question right. Chemical formula for the following inorganic acids. Ooh, fun one. Nitric acid. So, we know that acid means that it has an H in the front, right? And we have nitric acid here. So, remember, it's itaic, itos. Well, we have an ic here, so we know that it's nitrate. So it's H plus, and then you have to remember, you have so, co, clo, no. This is my trick to memorizing them. You know, this is SO4 2 minus, CO3, 3 2 minus, CO4 minus, and O3 minus. And we know that eights are typically the highest number ones. So this is nitrate here. So it's NO3 minus. And this is positive, right? We know that this hydrogen is going to act more towards like the, not sharing. It's not the covalent side. It's more of the ionic side. So we know our trick. We want these charges to balance out. Positive charge, negative charge. H and O. We only need one of each. Sorry. H and O3. And that is our nitric acid. That is a chem exam right there. Let's see the recording time. I think the video time. I might crop out that part where I had the technical difficulties. But that's 54 minutes. So including the time that we spent doing the initial stuff, we were still able to finish the exam with plenty of time to spare. Again, make sure you take your time. And I hope that this was helpful. If you have any questions, I should be hosting a study night tonight. From I think I said 7 to 9:30. I might regret that. I might not. But we'll see. Anyways, this is Christian, signing out. Good luck on your exam, everyone.